Today we are going to prove Taylor's theorem. The way I've written it up here is in very succinct form. I don't have the normal stuff up there like for x in the domain of blah 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 and whatever, and there's this m there. What is that m? Normally when I write something up on the board I have all of that stuff out and then we finally come to the statement. But we'll get to all of excuse me, we will get to all of that in a minute. So first thing to notice though is this is the nth Taylor polynomial, or the nth Taylor approximation of this function. And let's think about what this means here, okay? That's the absolute value of the function itself and the Taylor approximation. So let's say that this is our function itself. There's f. And then the nth Taylor approximation, let's say that this here is x0. And we are going to say that, and obviously there is an x0 here. That's what we're talking about. And for this whole conversation, x0 is going to be some constant in the domain of f. And what this says is we have some kind of Taylor polynomial here. Here's the nth Taylor approximation. And what this thing says here is that if you are at some value x here, and so this distance from here to here, that distance is x minus x0 right there in absolute value. That's what that is. And this is telling us that the difference between the function itself at that value x and the Taylor approximation here, that is what this distance is. This bit right there. That's that distance. It's an absolute value because we don't want to have to change the sign if one's taller, if one's bigger than the other, right? Because clearly in the way that I've drawn this here, f is a smaller number than t. And so if you take the smaller number minus off a bigger number, you get a negative number. And we don't care if it's negative or positive, so we're saying the absolute value. That's the error right there. That's, remember, we called this the error. But that right there is that difference, f of x minus tn, the nth Taylor approximation at x. And what this says is that we could estimate that error, right? That error will be smaller than this quantity right here. We're going to wrap our minds around what that quantity means. But one thing about it is that when n gets really, really big, it does not matter what, we're going to get into what m is, and we're going to get into, well, it will not matter how big this is either. As n increases, this quantity goes to 0 as n goes to infinity, and we're going to prove that too. Your book does such a terrible job of proving it. I hate the way the book does it. We're going to do it true to Justin form. We're going to go way, way more in detail than we should need to, just to really drive this point home, because this is what this tells us here. That since this is true, this tells us that the limit as n goes to infinity of Tn of x is indeed the function itself. Okay? And that should be obvious from this. If you could make this difference, if you could make the error as small as you want, right? If you can make the error arbitrarily small, and it doesn't matter how big this is, then it must be the case that the Taylor approximation is approaching that. And we saw that a bunch of ways graphically and stuff like that when we were first talking about this stuff. So that's the goal for today. We are going to prove this statement first, okay? And then we're going to prove that this quantity does indeed go to 0 as n goes to infinity. So first off, this m right here. What is this m? Well, we're going to start with the n plus first derivative of f. Okay, so let's say this is the n plus first derivative of f on some domain a to b. It could be across its entire domain. I mean, it could be across all real numbers, but just for the sake of making this a little easier to see, let's just say that its domain is a to b, okay? Now, what we're going to do is take the absolute value of that guy, and then find the maximum value of that function on that interval, okay? That's what m is. Now, over here I've drawn another one, right? Y absolute value, you'll see in just a second here. So it doesn't matter this way whether the largest value it takes on is a negative value, like in this case. It could be that the largest value it takes on is a positive value. I mean, largest in magnitude, right? Like if this is -5 and that's +1, then -5 here would be the largest value it takes on. But when you take the absolute value of it, it's always going to be that positive number. Similarly, I've tried to draw this about the same. The absolute value of this guy here is this guy, and still the largest value it takes on is this big M right there. Now what this does for us here is, now we could forget about this thing. We're not too concerned with this right now, okay? So because what we get then is we could say then the function, the n plus first derivative of f, is bounded above by positive m, and it's bounded below by negative m. And it doesn't matter if it looked like this to begin with or if it looked like this to begin with, because again, the largest value, the most positive value, is it's bounded above by positive m, and it's still bounded below by negative m. Now, let's think about this. So, let's say then that we want to compute the integral of this function from over some 2 points. And let's call those 2 points from x0 up to x. Okay? So this is the integral that we want. We want this area right here. There's this positive area there. There's this negative area here. And we want to try to get a bound on that. Well, doesn't matter, and again, right, I'm going to go ahead and do this over here too. Let's say here's x0 up to x. And so then the area that we're trying to figure out is this guy right here. Well, in both cases, right, or in either case, however you want to think about this thing, once you've found what m is on this interval, you could say, well, this area, and let's go ahead and do this as an integral, right? So the area from x0 up to x, of this function. Now we're using x as an input, right? Or rather, we're using x as a variable up here. So it would probably be a good idea to go ahead and change this to be a t. And we think about this as the t-axis. Then this guy, the n plus first derivative of t dt. Well, it's got to be, regardless of how you look at it, it's got to be less than this area right here. Right? Right? So in other words, this thing has to be less than m, times that interval. Or if we want to do it as a integral, we could say, think of m as just a constant function, and then the area would be from x0 up to x dt, like that. And also, it must be the case, because now that we're down here below the x-axis, this is now negative area. And we could say, okay, must be the case that that area is a lower bound for it. Or you could see it over here too, right? We have a ton of positive area up there, a little bit of negative area in the green here, but nonetheless, whatever that green area is, it's got to be more than this negative area down here. And we could write that as an integral. Negative m. And we integrate that guy from x0 up to x dt. Everybody buy that? Right? So basically, in general, if you're trying to get a bound, you're trying to find a bound, an upper and lower bound for some integral, if you know that the function itself that you care about is bounded above and below like this and like this, then when you integrate, that all stays true, right? We've done this before. I'm just really want to get into this to make sure that you know, we're all on the same page here. Okay, so there's your visuals for all of that, but this should obviously be true. Okay, and this is where we're starting with. So that's what m is. Now let's see how we're going to use this and how that's going to help us get this guy right. So this is where we're starting. We're starting with the n plus first derivative of a function on some interval. So we have our n plus first derivative t on some interval a to b. And what we're going to do is take some fixed value x0 right there. And we're going to say, now you give me any other x in this interval. And this is going to be our variable right there. Okay, so x, we have some fixed x0, somewhere we know what the output is or whatever. And we want to know, okay, given any other x in that interval. We could, if we could say that this function is bounded between here and here, okay? So for instance, let's say that the n plus first derivative of this guy is, I don't know, sine t. We could say, well, sine t is bounded above by 1 and bounded below by -1. And that's true no matter where you are, right? And so any interval in there, doesn't matter what's happening, this thing is bounded above by 1, bounded below by -1, so we could plug in a 1 and a -1 right there, right? But now we're talking about in general, right? You have some function, you've found an upper and lower bound for it on that interval that you care about, in which you're evaluating your x0 and your x. And now we have this right here. Okay, so what are we going to do? How's this going to get us to Taylor's theorem? Well, we are going to integrate each one of these over that interval x0 to x. So we go from x0 up to x dt. We're going to do the same thing here. From x0 up to x dt. And here, from x0 up to x dt. Now I just left the negative on the outside. We could do that, right? It's a constant. We could pull it out. Okay, so what's the antiderivative of m dt? Well, again, right, if m is just a constant, it's just a constant function, its antiderivative, I guess, would be mt, right? M times t. And then we're going to evaluate that up at x and down at x0. Okay? All right. One bit at a time here. It's the antiderivative of the n plus first derivative of this function. It should be the nth derivative, right? Whatever it is, that's the n plus first derivative. So if you undo that, it must have been that guy right there. And so we're going to evaluate him up at x and down at x0. Okay, same thing over here. Oh, I didn't bring that negative along for the ride. Sorry about that. This guy now is just m. So its antiderivative is m times t, evaluated up at x and down at x0. So now let's do the evaluations. We have over here negative m times x minus negative m times x 0, like that, right? Just plugging in x for t each time, subtract it off. Okay, now what I could do, I'm going to pull out a negative m here. That should leave me an x minus x0, like that. If you double check that, that should work. Okay, now let's figure this out. So this would be the nth derivative at x minus the nth derivative at x0, like that. Okay. Finally, okay, this should be mx minus mx0, or I could just write that as mx minus x0, like that. Okay? Everybody buy that? Makes sense? Okay, now here's where this is a step that might be kind of hard to see. What I want to do again, what I want to do now is integrate again. Why? Well, because every time I integrate, I'm going to decrease the order of this derivative, right? Ultimately, we know Taylor's theorem has something to do with f itself, right? It also has something to do with all of its derivatives, etc. But the idea is eventually I'm going to need to get just f by itself. And the way that I'm going to do that is, well, since I have the nth derivative, if I just keep integrating, I'll eventually get back to f. And we'll have some other stuff too. But the thing to think about now is this is a function of x. This is a function of x. This is a function of x. I don't want to go ahead and integrate with respect to x because my bounds, I'm integrating, I want to keep integrating over that same interval from x0 up to x, just plain old x. And x is the thing that we're imagining is variable here. You know, coming back to our original picture, we have some Taylor polynomial doing this type of thing, and we're saying, you know, x could, this could be any interval in the world, and so that's what we want to wrap our heads around. The x is the thing that's moving, and so that's not the input axis. I don't want to name the input axis x. So right now, this step, it might seem a little weird, but what I'm going to do is say, okay, so this is true for any x that we want to plug in, any x in the domain. But let's change the name, okay? So right now, the way we're thinking about this is these are each functions. This is not a function, by the way. This is what happens once you've plugged in whatever this value is. If this value was 5, if x0 were 5, you'd plug that into some function and you'd have some output. That's just a constant now, right? This is a variable, that's a variable, that's a variable. So let's rename the input axis t. So now we have this type of thing. This is a t. We're just renaming the input axis. It's still true. Everything we have is still true. They're still just functions. And now we're just saying, okay, instead of putting x as your input, there's your t. And now we're going to integrate over this right here again. Okay? So I'm going to clear up a little bit of room up here. And let's do it one more time. So now, okay, I'm going to integrate here from x0 up to x dt. Integrate this guy from x0 up to x dt. And integrate this guy from x0 up to x dt. Okay? Everybody got that? Now here's the thing. I want to take a little break before we do this. And I want you to figure this out. T minus x0 dt. And let's say that k is some power. Any power except for -1. Except for -1. Pretend that k is any number that's not -1. And I want you to pause the video and compute this right here. Okay, one thing you might do is a u substitution, because you see that there's this inside of a thing, right? We have something inside of something, so you might think, okay, u substitution. Okay, and so the u is the inside stuff, t minus x0. So then what's du? Well, du is the derivative of this with respect to t. So the derivative of t with respect to t is 1, or as we call it, dt. x0 is a constant. Remember, this whole time, x0 is some constant that we chose. It's like 5. So you have t minus 5, take its derivative, should just give you 1, or as we do when we're doing this, it's just dt, okay? Okay, so let's replace this stuff. We have u to the kth power. dt is just du. We don't need to do anything fancy. There's just that, okay? So then the antiderivative of u to the k, as long as k is not -1, then it should be u to the k plus 1, and then we'd have to divide by k plus 1 right there. But u is not what we don't care about u, we care about the t, and so we get 1 over k plus 1 t minus x0 right there. And then we're evaluating this guy down at x0 and up at x. Okay, so let's do that. Have 1 over k plus 1, plug in my x, minus off, do the same thing, 1 over k plus 1 down at x0. x0 minus x0. Oh, nice. This goes away, right? x0 minus itself is just 0, so that's a big fat 0. So this just works out to be this. 1 over k plus 1 times x minus x0 to the, oops, I didn't write it up there. I didn't write the k plus 1. Sorry about that. Sorry about that. K plus 1 on the top. K plus 1, like that. Okay, everybody got that, right? And you could double check and to take the derivative of it and see, like, yeah, the k plus 1 comes down, kills the k plus 1. You bring it down to k, yep, you bring it down to k, and then there's the t and the crazy stuff like that, but you get the idea, right? Okay? All right, so that's going to help us here, all right? The negative m is just a constant, and we could just pull out that negative m. So there's negative m. And again, now this, and I'll go ahead and be explicit about it, this is what we're doing. This is just t minus x0 dt. And we could say, oh yeah, and you could do a u substitution when you see something like this. But if you see that this is just some, it's not like 2t minus 5, it's just t minus 5. So you know that if you let u equal that, when you take the derivative, dt is just du. You don't need to do any kind of crazy stuff. There's not going to be a t that, or a 2 that drops down or something like that. You could just pretend that this is just the variable itself. And so, okay, the antiderivative of that would be, I guess, 1/2. So minus m, we'd have a 1/2 t t minus x0 squared. Yeah, that's the antiderivative of that. Evaluated up at x and down at x0. Cool thing about it going down to x0 is that's just going to go away. You're going to, like, he's gone, right? And so really all we're doing is plugging in an x. Of course, we just did this, right? I just proved this in general that it's going to do that, right? This is the last time I'm going to go through and do this. We're just going to jump to the chase from now on. But at any rate, okay, so that guy, this integral works out to this right here. So let's do that. I'm just going to go ahead and write it down. Minus m over 2 x minus x0 squared less than or equal to, okay? Same thing over here. That m is going to come out, a 2 is going to go in the denominator. I'm going to have m over 2 x minus x0 squared, like that. Okay? Remember, this is a definite integral. There's no plus c here. The plus c would have come from this, but it happens to be that when we plug it in, we make that guy go away, and so that's why there's no like plus c here, in case you're wondering. Okay, now this part, this is where it's going to start to get a little complicated. The integral of this minus this is the same thing as the integrals minus blah, 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 like that. Now, each one of these gets a dt. This is a function of t. This guy is just a constant, right? You have some fn, and let's pretend it's like cosine. You plug in some x0, like let's say it's 5. You plug in some x0, and you get some output. This is just a constant. This thing is a constant. The same way when we first integrated m dt, we said, oh, that's just a constant, right? So, in fact, I'm going to be explicit about this, and let's go ahead and pull it out and say this thing is the same thing. So going from x0 up to x of f, the nth derivative at x0 dt, it's the same thing as if I pulled it out.
This the thing I like.
Okay. x0 up to x1 dt. Well, the antiderivative of that would just be t, and he would be evaluated up at x and down at x0. So that would be x minus x0. And then he's just multiplied by this right here. So this is the same thing as negative the nth derivative at x0 times x minus x0, just like that. This guy, so he's a function. He's a function of t. We're integrating with respect to t. And so its antiderivative must be 1 power less, right? It would be the f in minus first derivative. And we're going to evaluate him up at x and down at x0. So that gives me f, the n minus 1th derivative at x, minus f, the n minus 1th derivative at x0. Now, minus the nth derivative at x0 times x minus x0. And we're saying that's less than or equal to m over 2 x minus x0 squared. And it's bigger than negative m over 2 x minus x0 squared, like that. All right, let's keep going. So this is where we left off. We're going to integrate again. And in order to do that, since we're integrating from x0 to x, we're going to rename the inputs t. And so here's a t. x0 is just a constant. This is just a constant. This guy's a function. There's t. This guy is a function. It's an input variable. We're just changing the name of the input variable. So now let's do the same thing again. We're going to integrate with respect to t from x0 up to x dt. we're going to do that each time here. And so we go from x0 up to x dt. From x0 up to x dt. Finally, from x0 up to x dt. This guy too. We're going to integrate from x0 up to x dt. Now, negative m over 2 is a constant. He comes out. We know the trick here. We're just going to raise it up to the third power, right? It would be t minus x0 raised to the third power. We'd have to divide by 3. But then we're going to evaluate up at x and down at x0. And so when we do that, the x and the x0, the x comes in as 1/3 x minus x0 minus 1/3. Oh, it's a big 0 because you're plugging in an x0 minus x0, so it's gone. So it's just that. Don't forget about the negative m and the 2 there. And so what this works out to is negative m over 3 times 2 x minus x0 to the third. All right. I'm going to get this guy over here. Same trick, right? We could say, okay, the m and the 2 stay put. The 3 comes into the denominator. You do the thing and you subtract off, and what you end up with is an x minus x0 cubed, like that. Yeah? Okay. Now the hard part. This is a function, right? He's not a constant because t is the variable. And so the antiderivative then would be f, instead of n minus 1, it would be n minus 2. The n minus 2th derivative evaluated at x. Then subtract off the n minus 2th derivative evaluated at x0. Now, this guy is very much like what we had before, only now it's the n minus 1th derivative at x0 dt. He's a constant. We could pull him out. Integral dt, right? So then that just works out to whatever the constant is, just some constant number, you plug something in, and what you end up with is a t evaluated down at x0 and up at x. And so this works out to f x0, n minus 1th derivative. Now, plug in your x and you get x, subtract off, plug in your x0, you get x0. So that works out to just that guy right there. So that's minus this is minus this right here. So minus the n minus 1th derivative at x0 times x minus x0, like that. Okay, now this other one, let's see, that fx0 to the nth derivative evaluated at x0 is a constant. So I'm going to pull him out. Now we just have t minus x0 dt evaluated from x0 up to x. We just did this, right? This we can pretend is just a u, and so we'll go 1/2 u squared when we take its antiderivative. Plug in an x, you get an x. Plug in an x0, goes away, and so we end up with the nth derivative x0. This works out to 1/2 x minus x0 squared, like that. So I could clean that up a little bit. I'm going to write that as the nth derivative evaluated at x0 over 2 x minus x0 squared, like that. That's what that works out to. So, and it's again minus, right? Because it was minus each one of these. So it should be minus the nth derivative evaluated at x0 divided by 2 x minus x0 squared, right there. You starting to see what's going on? Let's do one more and see if we can come up with a pattern, okay? So this is still true, provided that each one of these derivatives is continuous. At least in our class. Because in our class, remember we said in order to take the integral of some function, we say that that function has to be continuous. In our class, we say that. And so, provided that each one of these n derivatives, the nth derivative here, provided that that's a continuous function, we could just keep doing this all day, and indeed we're going to, right? And everything should work out just fine. So let's continue on, okay? Now, I'm about to integrate, and there's going to be an x up here, so I don't want x to be what we're calling the input axis. So everywhere that I see just an x, I'm going to replace it with a t right now, okay? So we're just renaming the input axis. Instead of being x, it's going to be t, 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 and t. Now, let's integrate with respect to t from x0 up to x. From x0 up to x, dt. Oh boy. I'm not going to write my dt's anymore. I'm just going to do this, x0 up to x, here, 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 x0 up to x, dt. Okay, here we go again. Got a bunch of constants out front, so I'm going to pull them out, minus m. We have a 3 times a 2. That would have to go up a power. So it's going to be whatever that is to the 4th. Okay? But we need a 4 in the denominator down here. Right? That would be a t. Then we evaluate at the endpoints. You plug in an x and you would get this. Then you subtract off, you have the same thing, blah, 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 x0 minus x0 to the 4th, but that guy's a big fat 0, so he goes away. And so that's what we're left with right there.
Stop walking to me!
Okay? Now, this is a function, and we're integrating with respect to t, so that's good. Its antiderivative must be the n minus third right there. Then we're going to evaluate, and that would be a t, and we would evaluate up at x and down at x0. So we'd plug in an x here, and then we'd have to subtract off the same thing, n minus 3 at x0. Okay, so that takes care of that one right there. I'm going to go ahead and do this because this is going to get ugly in a minute. Now, that's just a constant. There should be no surprise now what's going on. This constant is then just this, and since you're doing this right here, you would have whatever that constant is times x minus x0, and so it should be minus f, the n minus second derivative evaluated at x0 times x minus x0, right there. Okay. This next one, so that guy's gone. This next one, we could pull out the constant and we're left with this. And so he would have had to have been a 1/2 t minus x0 evaluated at x and at x0. And zeros make it go away. Oops. Oops. Right. Double check. Take the derivative. Drops down to that. Yeah. Okay. So that would be 1/2 x minus x0 squared. X0 makes it go away. And so then we need that derivative, or that constant to come in. That's minus the n minus first derivative evaluated at x0 over 2 x minus x0 squared. Yeah? That was that one. Got it. Now, this one, pulling out that constant, gives me this integral t minus x0 squared. So now he's going to come up, get a 3 in the denominator. He'll go up to 3. The x and the x0 is going to leave us just with that. So I could rewrite that as minus the nth derivative at x0 over 3 times 2 times x minus 0 cubed. That should be that one. There's that. Now, finally, same thing happens over here. The only difference between this and that is that that one's negative, that one's positive. We would have m over 4 times 3 times 2 x minus x0 now raised to the 4th power right there. Now let's see if we can figure out a pattern. Okay? Instead of going through and actually doing the integrals and stuff like that, I think we can see what's happening. Every time we integrate this guy, we get another dude in the denominator, right? So next time, this would be x to the 5th, x minus x0 to the 5th. We'd have a 5 in the denominator. And let's jump to the chase, right? 2 times 3 times 4 times 5 would be 5 factorial, right? Same thing over here, right? You'd take the antiderivative, you'd end up with something raised to the power of 5. The 5 would have to come into the denominator, and we'd have 5 times 4 times 3 times 2, or 5 factorial. The next time we undo, we're going to end up each time, this guy is going to give rise to one less power, right? We'll have fn minus 4 now. He'll be at x minus n minus 4 x0. Now each one of these guys is going to pick up one of these factors, right? So he didn't have any factors before, he's going to pick up a new one. N minus 3 evaluated at x0 will end up with an x minus x0. The guy who already had an x minus x0, he's going to pick up an extra power. But we'd have to divide off by that power, right? So he comes down there, x minus x0 now squared. This guy will go up to cubed, which means we'll have to have a 3 in the denominator, minus f n minus 1th derivative evaluated at x0. Now we'll have a 3 times a 2 in the denominator, or how about 3 factorial? And he'll have an x minus x0 to the 3rd. This next guy will go up to the 4th, which means a 4 would have to come into the denominator, and so the nth derivative evaluated at x0 will have 4 times 3 times 2, which is times 1, which is 4 factorial. And now his power, x minus x0, will be up to the 4th power. And so on and so on. Let's see. So, okay. This, in case you haven't noticed, is a Taylor series, isn't it? This, in fact, what I'm going to do, I'm going to go ahead and pull out a negative and say, okay, this is fn minus 4x minus, 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 minus. Let's pull that minus out of each one of those and rewrite that. And so that's going to give me fn minus 4 x0 plus, right, pulling out the minus makes that a plus. That's fn minus 3 at x0, x minus x0, plus fn minus 2 at x0 over 2 factorial, x minus x0 squared, and so on up to the last one that we have, which in this case is the nth derivative. It's always going to be the nth derivative. It's minus x0 to the 4th. Okay, and so that's the n minus 4th derivative of f minus the, Is this, well, we're not quite to the Taylor approximation yet, but we could see that if we keep going, we're going to get there. Let's see if we can figure out a pattern now. Negative m over 5 factorial x minus x squared. So, okay. When it was n minus 3, we had our power out here, our bound was raised to the 4th power. When the biggest one was n minus 2, the power we had out here was the 3rd power. When it was n minus 1, it was the 2nd power. So, I'm willing to bet that this pattern continues, that it's f when it's n minus 5, then we'd have raised to the 6th power. And we'd have a minus m, we'd pick up an extra 6 in the denominator, making that there, okay? Now what's going to change here? Well, we're going to pick up an extra power here, right? Because those are going to match, and we would have fx0 n minus 5, and so on, all the way up to the last one, which is going to pick up an extra power, so it'll be f, still the nth derivative, at x0, but now it'll be over 5, x minus x0 to the 5th, and then this guy is going to pick up factor in the denominator, and he'll be raised to the 6th. Okay? Now, when it's n minus 6, it'll be to the 7th. When it's n minus 7, it'll be to the 8th, and so on until we get all the way down to n minus nth. Right? So let's think about that. We continue this on until we get the f, which derivative? The n minus nth derivative, or the 0th derivative, or just plain old f from the very beginning. Okay? So let's pretend we had continued that on. And what would we have? Well, it'll be the same order here. When it's n minus n, it's n minus n. So he's f x0. And then what happens? Well, it would be the next higher derivative, right? So, like, if n were 5, 5 minus 4 would be the first derivative. 5 minus 3 would be the second derivative. 5 minus 3 would be the, whatever, you know what I'm saying. I think that should have been a 2. Anyway, and so on and so forth. So, then the next one would be the first derivative at x0. X minus x0, then it would have been the second derivative, x0 over 2 factorial, x minus x0 squared, all the way down to, let's make sure we haven't messed this up, right? When it's n minus 5, it's a 5 here. When this one's n minus 4, he's a 4 there. When he's n minus 3, he's a 3 there. So when he's n minus n, he should be an n here. So then, nth derivative, x0 over n factorial, x minus x0 to the nth power. Now, okay, now the outside stuff. N minus 5, you get a 6. N minus 4, you have a 5. So n minus n should be one more, it should be n plus 1. So minus m over n plus 1 factorial, x minus x0 raised to the n plus 1. Positive m over n plus 1 factorial, x minus x0 to the n plus 1. Lo and behold, that is the nth Taylor polynomial of f evaluated at x0. And so, what we just found was that this is less than or equal to fx minus the nth Taylor approximation evaluated at x0. That's all that is, right? Which is less than or equal to positive m n plus 1 factorial x minus x0 to the n plus 1. Now, this is what we wanted to show. Because think about it, right? Like you have some, let's say x minus y is between, say, minus 5 and 5. That means the same thing as x minus y is less than or equal to 5, right? That's our rules for these guys. This means that in absolute value, this thing is bounded, which means it can't get bigger than 5, and it can't get less than negative 5, right? We should all remember this. And so, that right there means the same thing as this. That the distance from the nth Taylor polynomial to the function itself at some value of x n plus 1 factorial, and I'm just going to throw him in the numerator. The only thing that looks a little different is that this, when I wrote this up earlier, that was an absolute value. So why isn't it absolute value here? Well, I was implicitly assuming when we first started this off, we said that this is bounded above and below. And then when I did this thing right here, we integrated with respect to t from x0 up to x, from x0 up to x, from x0 up to x. Remember, m was a positive number, okay? And as long as x is on the right-hand side of x0, then x minus x0 is a positive number. But if I had drawn this differently, like that, and this is what we want. We want it to be the case where it doesn't matter on, like, you don't have to go to the right-hand side of x0. We want it to be true if you take x to be on the left-hand side of x0 too. But if I had done that, then I would have needed to integrate it the right way. I would have to go from x up to x0, like that, right? And then each one of these delta x's would be a positive number, right? And so, if indeed it were like this, well, the way that we did this is all of the zeros were on the bottom, okay? But then that doesn't quite make sense, because then this is a negative negative, and you know what I'm saying? So like, if you integrate, you have negative m, and you go from 2 up to negative 2, that's the same thing as flipping them and making it positive, right? Negative 2 up to 2. And so we assumed that x was smaller, but if it had been the case that I chose an x over here, well, I would had to have flipped all of them. And then in doing that, I would essentially be multiplying through by a negative. Right, I'd say, oh wait, hold up, I need to flip all of these, which makes this negative, makes that a positive, makes this negative, and makes this negative. And then it's like, well, hold up, you have a positive, that's less than that. Oh, you should have also flipped each one of these too. Yeah, and then you could just rewrite it the original way. And so what this does is it says, well, I'm going to say, if it had been negative to begin with, you would have done some stuff to make it so that it doesn't do this. Your positive number is less, and you're blah, 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 blah. So rather than going through and talking about all that, I just save it for the end, and we're going to say, obviously, if you were integrating the other way around, then whatever. Like, another way of looking at this is an absolute value of something. It has to be positive or zero. At most, it could be zero, right? Or at least it could be zero. You can't get any lower than zero. And so if you happen to choose, let's say you have an x minus 5, your x0 was a 5, and you're raising this to some positive power, well, obviously, if you choose like a negative number, like -2, well, then you have -7 raised to the third. That's a negative number. It doesn't make much sense to then say you have some negative number and now you have an absolute value that's less than that, but it can't be because it's always positive. So this is just a way of saying, you know, we could figure out whether it's positive or negative, and then we would have changed our limits of integration to begin with, and we'd still end up with the same thing. So this is just a way of saying, okay, this guy's got to be positive. Okay, it's the absolute value of that right there. But this is what we wanted to show. Okay, this is right here. This is Taylor's theorem. Okay, or at least what I'm calling Taylor's theorem. Your book does it a little bit differently. It defines it a little bit differently. This is a much more straightforward way of saying it. Now, my claim is that no matter how big M is, no matter how big this is, let's say your x0 is a 1, and you want to take an x out here that's bigger than like 10 to the 10 to the 10, right? My claim is, even if that's the case, and your x minus x0, which would be x minus 1, which would be something much, much bigger than 10 to the 10 to the 9, a really, 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 really huge number. And m can be arbitrarily large. M itself could be like 10 to the 10 to the 10, and then you have some 10 to the 10 raised to n plus 1, and you're going n plus 1 factorial. My claim is that even in that really, really, really bad scenario, when n goes to infinity, this thing still goes to 0 as n goes to infinity. So that's going to be the next thing that we prove. Alright, pop quiz. The limit as n goes to infinity of 1 over n equals... That's right, big fat 0. Now what does that mean? Let's think about what this means. This says that you give me any tolerance, right? Any epsilon bigger than 0. Then I can make the difference between this function and this function, this number, less than that. Tolerance, right? That means that, well, actually it means for this, then there exists an n, also positive, a big N, so that this is true whenever little n is beyond it. Okay, so again, think about how this is similar to what our thing here. Okay, we have a m, this is n plus 1 factorial, blah, 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 right? Saying the tolerance, the error between these two functions can be made arbitrarily small. Same kind of thing here. The error between this function and 0 can be made arbitrarily small. Now, let's just think about this. Like, so, in order to prove this thing, right, this is the same thing as this, right? And when n is positive, we're going to assume to make n positive, okay, so we have this, okay? So then I could bring the n up here, and so 1 over epsilon less than n. So whenever n is bigger than 1 over epsilon, I could guarantee that this is true, right? That's how we could, that's how we know that this statement is true. So for instance, you say, I want to make sure that this is less than 1/100th. Then what you do is you say, okay, well then if n is bigger than 1 over 100th. In other words, that should be 100. So whenever n, this is my big capital N, we say that whenever little n is bigger than that, then I guarantee that the difference between 1 over n and 0 is less than 1/100th. And that should be pretty obvious, right? So this is what we're going to need to do. We're not going to be as formal as this. But my claim is that I could find an n large enough so that you give me any m and any number here, and I could make this as small as I please. That's what I'm going to try to, that's what we're going to show right now, okay? So first things first, I'm not gonna do this with n plus 1 because that's just annoying, right? It's gonna be easier to work with just n, and if really this should be the same thing, right? If k equals n plus 1, then you could imagine as k gets really big, n plus 1 gets really big. If n plus 1 is getting really big, k is getting really big, right? So I think if we prove that this goes to 0 as n gets really large, then I think you believe that this also goes to 0 when n gets really large. Let's not split hairs here. It's just going to be easier to deal with n instead of n plus 1. Okay? So let's start off here. Let's say that you have this set up. You had some function, you found what m had to be on some interval, and right now you've found your x0, maybe it's 0, and you have your x that you want to do. So, like for instance, we had an f of x is like a cosine x. And we said, well, m could be 1 because it's always between -1 and 1. And so we could take that as my m and my negative m, right? And we bound the function. And now we're saying, okay, maybe I've found the Taylor series at 0 for cosine, right? Like, we could say, oops, my Tn of x is then 1 minus x squared plus x, oops, over 2 factorial over 4 minus x to the 6th over 6, and so on. And we want to know, okay, I want this thing to approximate the real thing all the way out to, let's say, like 100,000. Okay, and so then my x minus x0, right, this guy right there, would be 100,000 minus 0. And so this is 100,000. Okay, so now my setup, I have my m is 1 times 100,000, and I'd want to know what number what n do I have to take in order to make this smaller than some tolerance, right? Like I have my f minus my Tn, and I'm saying I want to guarantee that even all the way out there at 100,000, this is less than like 0.01. I want it to be within 1/100th of the truth, right? Because you know that this thing is going to eventually break off like that, right? We saw that before. As you start doing these, eventually it'll conform for a while, but then it blows up. We want to make sure he's within 1/100th before he blows up, okay? And so the question is, for what value then? Well, what you do in practice is you would just plug in bigger values of n. You would put this in the calculator and just plug in bigger and bigger values until this thing gets small enough. That's how you would practically do it. You're not going to do what we're about to do to prove this thing in general. You would just plug in values until it gets good enough, and then you plugged in, let's say you got all the way up to, like, let's say n equals 1,000,000. Then you could guarantee as long as you have all the way out to 1,000,000, then you're good to go. and your Taylor approximation will be within 1/100th, even all the way out here at 100,000. Please keep it down. Thank you. So, that's the idea here. That's what we want to do. So, what we're going to do is we're going to imagine we found an m, okay? And we found whatever that is. Now, what I want to do is say, okay, what I want to do, I'm going to let b equal the ceiling of this value right here. What does that even mean? Well, let's say that that worked out to be something like, I don't know, 10 minus pi over 2. And whatever that happens to be. That's like 8 point something, I don't know, like 8.6210. What I'm going to do is say, okay, take the ceiling. That is the next biggest integer. In that case, would be 9, right there. Okay, so you take whatever this is. If he happens to be an integer, like if it's 10 minus 3, then you'd say, oh, okay, it's just 7. It's just an integer already. But if it's something like 3.1, 6.1, you just take the ceiling and say, okay, it's just the next biggest integer. Okay, so that's what I'm going to do. I'm going to say, let b equal the next biggest integer, right there. Okay, well then, this m b to the n over n factorial is then either, if it happened to be an integer, then they're equal. But if it's like 2.7, now we're up here at 3, and so this value is bigger than that value. Right? Yeah. Now my idea is what I'm going to keep doing is I'm going to find a bunch of successive things that this is less than. And then what I want is to be able to find some expression dependent on n that I could make as small as I want. That way you give me any tolerance, like 0.01, and I'll be able to say take n large enough so that this is indeed smaller than that. That's the name of the game here. That's what I'm going to do. Okay? But before I do that, let's just look at this part right here. b to the n over n factorial. Let's play with this a little bit and see what happens. Because right off the bat, especially if b is a big number, if b is a small, and so that's one of the reasons I'm using b, is because we're imagining it's really big. Because if b were really small, like, I don't know, this isn't necessarily small, but if this were the case, this is not that hard of a problem to figure out. You could say, well, hold up, let's just keep using bigger numbers for n. So when n is equal to 2, you have this. That's not very small. But if you keep going, let's say that n is 3, and you have 3 here. Now we have 8 over 6, not quite there yet, but if you keep going and do this, now the denominator's starting to get pretty big, right? We have, what's that, 16 over 4 times 3, that's 24. So the denominator's starting to blow up, right? And we can see that as I start putting bigger numbers of n, eventually this guy gets much bigger, because the 2 is staying put, but now we're doing a 6. The 2 is staying put, but now we're doing a 7, right? And you could imagine, keep doing this on and on and on, and eventually you're at like 10,000. Do another 2, and now you're at 10,001. And now the denominator is getting much, much, much bigger. And it's easy to see when you have small numbers that it's not going to take too long before you can make this denominator big enough so that you can make it less than your tolerance, say 0.01 or whatever it is that is your tolerance. Okay, so we're imagining that b is a big number. Okay, now let's just start. Let's just see what happens when n is equal to b. What do we have when n is equal to b? Well, on the top you have b times b times b times b. How many times? Well, I guess b times. And on the bottom you have 1 times 2 all the way up to b. Right now I could see the numerator is bigger than the denominator, right? That was the case even when b was 2, right? We had 2 times 2 over 1 times 2. Numerator's big, okay? We're not getting a handle on it yet. We want the denominator to be really big to make this thing small, okay? So we're not there yet, so let's keep going. What happens if n is, say, b plus 1? Well, then you're just basically, you just get one more b up here, and now down here you have a b plus 1. Okay, let's keep going. What happens if n is b plus 2? Well, you get one more b up here, and now down here you have a b plus 2. Now, something tells me if I keep going, eventually this thing's going to get really, really, really big. Big enough. What do you mean big enough? Well, let's just see what happens. Let's say that we kept going until we got n went up to b plus 1, b plus 2, all the way up to b plus b. Okay? Then what's that going to look like? Let's see. Well, we went b plus 1, b plus 2, all the way up to b plus b. And for each number we have in the denominator, there's exactly one b in the numerator. Okay? So we're up here at b plus b. Now that's the same thing as 2b, right? Now what if it were one more? What if we took n to be even bigger? What if we did 2b plus 1? Well, then we'd have a 2b plus 1. And we'd have one more b in the numerator. Okay, and then we went 2b plus 2, 2b plus 3, 2b plus 4, and so on, until we got all the way up to 2b plus b. Plus b, or in other words, 3b, right? And what if we kept going? And for each one of those, we'd have one of these, and we could keep going. Right? That's the same thing as 3b. So 3b plus 1, and so on, and so on. And what's going on? Well, let's just think about this. Okay? Remember what I said I was going to do. So I was going to get a series of inequalities. We already did this once, right? We said, well, this is less than that, right? Now what I'm going to do is come up with another one. And remember, there's a few different ways we could make a fraction, make a bigger fraction. One way is if we made the top number bigger, right? That's true, just make the top number bigger. But we could keep the top number the same, and if we make the denominator smaller, then we end up with a bigger fraction. So that's what I'm going to do here. I'm going to say this thing right here, if I make the denominator smaller, then I end up with a fraction that is bigger. So I'm going to go ahead and do that right now. I'm going to say this number, remember we don't care about the m yet. We're just trying to get a handle on this. I'm going to say this is smaller, I'm sorry, yeah, this is smaller than what I'd get if I had made the denominator smaller. So I'm going to make the denominator smaller here in just a second. So here's the 1 times 2 all the way up to b right there. Now for each one of these, all b of them, because there's b plus 1, plus 2, plus all the way up to plus b, each one of those I'm going to make it smaller. I'm going to take off that plus right there. So that this is just b times b all the way up to b. And for every one of those, there's one of these on top. B times b all the way up to b. Now here at 2b plus 1, 2b plus 2, 2b plus 3, all the way up to there, I'm going to make each one of those smaller too. I'm going to say, okay, instead of 2b plus 1, it's just going to be 2b. And instead of 2b plus 2, I'm just going to make it 2b. And all the way up until I get to the last one, which is just 2b. Now the next one, instead of 3b plus 1, and so on and so forth, I'm gonna chop off that 1, chop off the 2, so 3b plus 1, 3b plus 2, 3b plus 3. If I make each one of those smaller and just replace it with a 3b instead of a 3b plus 1, and then a 3b instead of a 3b plus 2, and so on, all the way up to 3b, then I've made the denominator smaller, which makes the entire fraction bigger. And for each one of these things, we have exactly one b on the top. Okay, so the 3b pairs with 1b on top. The 3b pairs with 1b on top. All the way up to this b pairs with one of those. And what I'm going to keep doing here, I'm going to keep going until n is equal to, how about k b plus b. Okay, so what I was doing here is I kept going until did each one of these, and we went up to kb, and then kb plus 1, all the way up to kb plus b. And that was my last set of b terms in the denominator here. All right, there's your b terms right there. B more terms right here. Now what I've done is each one of these I've taken off the plus 1, okay? And I've taken off the plus 2. So now what we have is just kb. Not kb plus 1, we have kb. Not kb plus 2, we've just made it smaller, it's just kb. All the way up to kb, like that. Each one of those is paired with one of these. Denominator. Okay. Now, let's see what we can do. What's really nice is we can see, at least from here on, right, that one of these b's cancels out with one of these. This cancels with that. This cancels with that. This cancels one of those. This cancels one of those. And so on. Right? All the way up until here. And now we have b, 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 b. So now this is the same thing as we have b times b, a total of b times. There's nobody else in the numerator. Now what do we have in the denominator? Looks like we have a 1 up to b. So that's b factorial, right? That's 1 times 2 times 3 all the way up to b. That's the same thing as b factorial. This is just 1 times 1 times 1, a total of b times. This is just 2 times 2 times 2, a total of b times. This is just 3 times 3 times 3, a total of b times. And so on, all the way up until I get to k times k times k, a total of b times. So my camera died, and I'm not sure exactly where we left off here, so I'm just going to go with this. Okay, we got to the point where we said that if n was equal to kb plus b, then we could take this, write it all out, and then remember we made the denominator smaller to make the whole thing larger, and we ended up with this expression right here, okay? And k, remember, was just some number. We were counting. We got up to 2b, then 3b, then 4b, then we got up to kb, and then we did our kb plus 1, kb plus 2, all the way up to kb plus b, and then we made each one of these smaller, so we had a bunch of kb's in the bottom, right? And then we did a bunch of cancellation, and this is what we ended up with. We had that the first b terms at the top, b times b times b times. That's stuck around there. But now what we've ended up with, or what we end up with now, is we get 1 to the b, 2 to the b, all the way up to k minus 1 to the b, k to the b, which we could rewrite as just 1 times 2, blah, 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 all of that raised to the b. And that right there is just k factorial. Now, you might be weary to say, well, hold up, this numerator could be really, really big. Like, yeah, but that k is arbitrary. We can pick k as large as we want. So it should be the case that no matter how small we want to make this, we could just take k big enough. Right? Now that's the only variable we have, right? We started off with a variable in the top and a variable in the bottom. Making it bigger made both the top and the bottom bigger, but now we've shown that's less than something that just has a variable in the denominator, which we can make bigger, make the denominator real big, you make the entire fraction really small. So this should give us what we're looking for, okay? I'm going to rewrite this here so I don't forget what that is. N equals kb plus b. Now, so, okay, we've shown that b to the n over n factorial is less than this expression right here. Therefore, we could say m times b to the n over n factorial is less than or equal to m times this expression right here. b factorial, k factorial to the b. Now what we want to show. Oops, I wanted to keep that around. N equals kb plus b. Now, what we want to show is that given any tolerance, that we can make this as small as we please, right? That we can make, by taking k to be big enough, we can make this, we can make this expression smaller than that. And is that true? You should be able to just look at it and see, like, yeah, the only thing that you need to change is in the denominator. Make that big enough, it should do it. But let's be really explicit here. Let's just make sure. M b to the b over b factorial times k factorial raised to the b less than epsilon. We could just do a little bit of manipulation here. Bring the epsilon down into the denominator. B factorial, bring the epsilon down, and bring that k factorial to the bth power into the numerator, right? Just brought him down, brought him up. Now, this should also be pretty obvious that that works, but let's just go ahead and take the bth root of both sides, right? Whatever b is, we'll just take the root. Let's see what we get. K factorial over here. Now, there's a couple ways we could do this. I'm just going to leave it like this, actually. That's fine. So the bth root of m times b to the b over b factorial times epsilon. Now, let's just recall, right? That b is dependent on this. Once you figure out what you're trying to do, right? M is a given, right? He's some constant number, he's the max. This is some number, and b is just the next biggest integer. So you have all of those. Then, given any tolerance, right, you just take each one of those numbers, plug it in, take the bth root of it, and then all we need to do is say, well, can I find a k that's bigger than that, right? So like, for instance, let's say that you do this calculation and out pops 100, okay? Well, then we could find such a k. 1's not going to work, 2's not going to work, 3's not going to work, 4 is 24, but 5, if k is equal to 5, then I believe that's 120, and so you could find it, right? And that's the idea. You could just keep going until you find one that's big enough. It doesn't matter how big this number is. This could be 100 to the 100 to the 100. And eventually, you could take a k big enough so that it is bigger than that number. So it looks like we got it. This is what we want, right? And we could see that, right? So all we need, so now you might be a little pedantic about this and say, Well, hold up now. The definition was that the limit, because this is what we're trying to show, the limit as n goes to infinity of this stuff here, m x minus x0 raised to the n factorial, we're trying to show that that's equal to 0. In order to do that, we need to show that the absolute value, m x minus x0 raised to the n, we need to show that for any positive epsilon, there exists an n so that the difference between those is less than epsilon whenever little n is bigger than big N. We found a k. Okay, so let's kind of figure that out. Remember, we had the bth root of b to the b. There was a b factorial down here, epsilon, and then what was this? Was that there's the b factorial, the m, right? And so we said, okay, we could find a k that makes that true, right? And so, okay, let's just think about this. You find that k, we just need to show that such a number exists. Can we find a big capital N that makes this true? So let's say that you found your k like we did a second ago. We found that when k equals 5, it's good to go. Well, okay, let's think about this. So we found our k. We said that there's some number, like in this case it happened to be 5, so we could say whenever k is bigger than 5. But we'll just call that number, about lowercase m. We found our lowercase m, which says, okay, whenever k is beyond m, then this is true. Whenever this is true, which makes the thing that I actually care about less than epsilon, which is the thing I'm trying to show, right? And so now we found this m, the m exists, but we need an n, let's see. So let's multiply both sides by b. We get b little m less than b times k. Add b to both sides. B little m plus b less than kb plus b. And we could say, oh, okay, then whenever, if we take this to be our big N, and since that's the same thing as n, we could say, okay, then I found an n. There's the n that we're the big N that we're looking for. And whenever little n is bigger than this big N here, then this will be true. This will be true, which makes this true, right? And therefore, that's true. And since that's bigger than that, that's bigger than that, and that gives us what we are looking for. So it is the case that the limit as n goes to infinity of m x minus x0 raised to the n all over n factorial is indeed equal to 0. No matter how big m is, no matter how big, we call it b, but back here, no matter how big that difference in absolute value is, that is true. Putting it all together then, we get that since f of x minus the Taylor approximation of x is less than m x minus x0 to the n plus 1 all over n plus 1 factorial. You know, I could rewrite this. I could call this n minus 1, and I could call this n whatever. It should be obvious that if that's true, that if this happens, it doesn't matter right there, right? Therefore, the limits of both the limit and that's supposed to be less than or equal to, so n goes to infinity, m x minus x0 n plus 1 factorial, but that limit is equal to 0. And this, since it's an absolute value, is bigger than or equal to 0. So that's bigger than or equal to 0. And so by the squeeze theorem, we have that 0 is less than or equal to limit as n goes to infinity of f of x minus n x, which is less than or equal to 0. Therefore, that limit is equal to 0. Which means the same thing as saying the limit as n goes to infinity of the Taylor approximation is the same thing as f of x. We just have to make sure that all of our derivatives, so this is true whenever each one of these derivatives is continuous, because if it weren't continuous, we couldn't have taken the integral of it, right? But so that each one of them is continuous, and really the only one, we only needed one of them to be bounded, right? We needed this, we needed the n plus first one to be bounded like that. But of course, if we're talking about letting n go to infinity, you are talking about infinitely many. So you're going to need all of your n plus 1s really to be bounded here. Otherwise, so if it's continuous, it's bounded, right? Usually. I can't think of a counterexample to that. But that's Taylor's theorem. Now we've proven it, right? Now we could say unequivocally that e to the x is equal to the sum as k goes from 0 up to infinity. In other words, the limit of the sum of x to k over k factorial. We could say unequivocally that sine x is equal to the sum as k goes from 0 up to infinity of x to the 2k plus 1. Oh, we need a negative 1 in there. Okay. Over 2k plus 1 factorial. We could say for certain that cosine x is equal to k goes from 0 to infinity. Negative 1k, x to the 2k, all over 2k factorial. These all work, right? Because in each case, every one of the nth derivatives is continuous. And given any interval, right, where do you want to evaluate your x? I don't know, since obviously what's happening here is my x0, I've chosen to be 0. Well, depending on how big you want your x, let's say you want your x to be 3,000, right? Well, that's going to make that x minus x0 n plus 1. That's going to make that equal to 3,000. And so you need to take a pretty big n. It won't matter because eventually, once you get out far enough, you go out to infinity, and it'll always be bigger than any x that you could come up with. And so each one of these is indeed equal to the function that it approximates. Each Taylor series is equal to the function itself.